In this video, I want to take a look at the solving of both exponential and logarithmic equations. I'm going to start with exponential. And with those, well, with any of these types of equations, there is no one solitary technique, one single procedure that I can give you that will work for all of them all of the time. A couple of properties, a couple of mathematical properties, though, that can be used to your advantage is, first of all, the property says a to the x equaling a to the y will always imply that x is equal to y. All right, now what's happening here is not something like a cancellation of the base of a. All right, the a's are not canceling out or something like that. What you're doing is you're taking advantage of the fact that exponentials are 1 to 1. Therefore, if two exponentials are equal and the bases are the same, then the powers have to be the same. This is a double implication. It actually works both ways, but we're going to mainly put it to use in this left to right hand direction, the one that says a to the x equaling a to the y will always imply x equal y. So again, that is just making use of the one-to-one property of exponents. An example of that being used would be to say, if you have 2 to the x equaling 32, if we can just get the bases the same, then we can assume powers are the same. Now, if you remember that 32 can be achieved by raising 2 to subsequent powers, like for example, 2 to the third is 8, so that's not what we're looking for. 2 to the fourth is 16, so that's not what we're looking for. 2 to the fifth is 32. So this can be rewritten as 2 to the x equaling 2 to the fifth. And once it's rewritten in this fashion, that's when this property can be used. We can now assume, safely and correctly assume, that as x is equal to 5. So again, if it is possible to make the bases match, then the powers have to match. So another example of that, if you had something like 5 to the 4x minus 7 equaling 125, again, if you can just get the bases to match, then you know the powers match. So once again, if you take 5 to the second power, that's only 25, that's not it. 5 to the third power is 125, that's the one we're looking for. So 5 to the 4x minus 7 equals 5 to the third power. And once again, now that the bases match, the powers have to match. So 4x minus 7 must equal 3. So 4x must be 10. X, therefore, is a 5/2. All right, so again, the property says if you can make the bases match, then the powers definitely match. Let's do that one more time. Actually, I was about to move on, but I see another good problem. If I had a 3 to the power x squared plus 4x equaling a 127th, once again, if I can just make bases match, I can make powers match. Now, with that 127th, what you're going to discover, if you go 3 to the second, and if you go 3 to the third, and you go 3 to the fourth, you're not going to get a 127th, but you did get the 27th, right? The fact that there's a fraction involved, something that sort of hints towards is there might be a negative power involved, and therefore these positive powers that I'm using here aren't going to get me there. If I go 3 to the power negative 3, of course the calculator is going to spit out an ugly decimal, but if I ask it to turn it into a fraction, there's my 127. So 3 to the x squared plus 4x is equal 3 to the negative third power. Since the bases match, the powers have to match. I'm going to set this equal to 0 because it's a quadratic. I'm going to factor it. And this one, unlike the other two, which is the reason I kind of like this problem, is it got 2 solutions instead of 1. And just to show you, that's a possibility. It just happened. Both those answers, if you plug them back in, they're going to work. All right, now, this is how you work the problem if it is possible to make the bases match. That's not always going to be possible. It's not always going to work out that way. If I had something like a 2 to the x equaling 40, you can sit there with your calculator all day and put in first power, second power, third, fourth, fifth, or whatever. You're not going to get a 40. You're not going to get a 40. So your alternative would be to simply take the log of both sides. Remember, the properties of logs say that if you had the log of 2x equaling, let me actually write that a little bit more neatly. It doesn't look quite right. We have log of 2 to the x equaling log of 40. Now that there's a log involved, the x can move down front as a multiplier. And you can simply divide off log of 2. And your answer will be log of 40 over log of 2. And that's actually a nice, perfect, exact answer. If you want to know, well, approximately what does that look like in decimal form? Well, on your calculator, just make sure you key it in right. It's log of 40 entire expression divided by log of 2. So that's about a 5.32. If you're the kind of person who likes to see it in a decimal form, that's what it would look like, right? Again, if I was able to make these bases match, I would, but I can't, right? Now, with that type of problem, you have to bear in mind is that on occasion, some logs are better than others to use. I used base 10 here because in this problem, it didn't matter. It didn't matter which base you used. In other problems, there are definitely bases, some that are better than others. So if I had an e to the 4t equaling a 200, you're never going to take a 200 and write it as a power of e. So with this one, what I'm going to do is take the log of both sides. And since exponentials and logs are both 1-to-1, that's why I'm able to do it this way. So taking the natural log of the left and taking the natural log of the right. Okay, this time I chose natural log. I didn't choose log 10. I chose log base e because natural log and e to the power are inverses of each other. So this will bring down nothing but a 4t. When I divide by the 4, I get an exact answer, which you can turn into a decimal if you feel like doing so, all right? But again, this time, since there was an e in the problem, I chose natural log. If there was a 10 base in the problem, I would choose common log. If you don't have either one, then choose whichever log you want. It won't make any difference. It will not matter in the final answer, okay? Now, some of these will have more than one base in them, which will make the problem a bit more complicated. If I had 5 to the x plus 2 equaling 4 to the 1 minus x, it would not really matter whether I use natural log or common log because there's not a base 10 or a base e here. So I'm just going to choose natural log, and that's just a completely arbitrary choice. You could have used either one, but that's just the one that popped into my head. Okay. Once again, powers come down as multipliers. Okay. Now I'm going to distribute through the parentheses. You need to look at the natural log of 5, and you need to look at the natural log of 4 and realize that they're really nothing more than just constants. They're just numerical values. And they can be distributed just like any other constant. So this can be x of natural log of 5 plus 2 natural log of 5 equaling, multiplying through here, natural log of 4 minus x natural log of 4. The next thing I need to do is get everything on the left that's got an x associated with it, and anything that doesn't needs to move to the right. So x natural log of 5 stays on the left, and natural log 4 stays on the right. X natural log 4 comes to the left, and 2 natural log 5 goes to the right. Okay, now everything with an x is on the left, everything without is on the right. Now what I can do on the left is factor out an x, and then on the right, I'm going to leave that alone just for a minute. Now I'm going to divide off the stuff on the left that I don't want. Canceling, I end up with natural log 4 minus 2 natural log of 5 over natural log of 5 plus natural log of 4. Now that is one form, only one form of the correct answer. Remember the properties of logs. Things can be written in a variety of ways, so expect that. For example, the 2 that's out front can be moved back up as a power, and 5 squared can become a 25. So there's a second way to write the answer. Subtraction can turn back into division. Addition can turn back into multiplication. So here's just 3 ways that this answer can be written. It's impossible to predict exactly what you're going to see in the back of the book. So be prepared for different options. All right, now one last type of exponential that you may run into. If I had an e to the x plus an e to the negative x equaling 4, first thing I'm going to do is going to rewrite this so that you can see the justification, the procedure I'm going to use. I'm going to rewrite this e to the x plus, this negative power implies a fraction. All right. Now that you can see that there's not just a fraction implied, it's directly written, maybe you'll understand why I'm going to multiply both sides by e to the x. And the reason is I'm going to clear the fraction. The right becomes a 4 e to the x. On the left, e to the x times e to the x. Be careful with this one. Remember, when you multiply like bases, you add the powers, and x plus x is 2x. And here you have cancellation. So that's just a 1. Okay, I'm going to move the 4 e to the x to the left. And this is the part that's often very hard for people to see. But what you actually have here is an equation of quadratic nature, of a quadratic type. Again, notice twice a 2 power here, a 1, and a constant on the end. Okay, this thing behaves like a quadratic in that sense. So I'm going to make up a dummy variable, so maybe it'll be more noticeable. I'm going to let u equal e to the x. That way, u squared will be an e to the 2x. This equation then becomes u squared minus 4u plus 1 equals 0. So now maybe you see that this thing is quadratic in its nature. So what I can do, since this won't factor, I wish it would, but since it won't factor, I'm going to use the quadratic formula. U will be equal to opposite of b, which would be a 4, plus and minus the square root of a b squared, which is negative 4 squared, minus 4 times an a times a c, all over 2a. This comes down to 4 plus and minus the square root of a 16 minus 4 over 2. 4 plus and minus the square root of a 12 over 2. Remember, 12 is 4 times 3. So taking the square root of 12 gives you a 2 square root of 3. And since a 2 will divide out everywhere, I can take it out. Okay, now is that the answer? Is that x? No, that's what u equals. And u is e to the x. All right, now remember that when you raise e to a power, you can only get positive answers. And note that 2 plus the square root of 3 is positive. And note that 2 minus the square root of 3 is also positive. So both of those answers will be usable. Okay, they're okay because they're both positive. All right, but what I have to do is solve for the x. And to get rid of an e, I use a natural log. So x is equal to the natural log of 2 plus the square root of 3, as well as the natural log of 2 minus the square root of 3. Okay, that problem's a little bit long, lots of steps involved, but what you have to get down to is the point to where it takes on the behavior of a quadratic. Okay, now those are a few examples of some exponentials. Let's look at some logs. Okay, logs are one-to-one as well. Okay, so for example, if I had something like log of x plus log of x minus 9 equals 1, what we want to do is use the properties of logs that we've learned to compress this statement down into a single logarithm. So addition will turn back into multiplication, and x times x minus 9 is an x squared minus 9x. All right. Now, since I have a log on one side and not the other, my technique, my strategy will be to turn this back into an exponential. Since it said log and didn't state a base, you assume it's a 10. So this statement will become x squared minus 9x equaling 10. Move the 10 to the left-hand side. Factor and solve. And something we have to make sure is that these answers will actually work. For example, if I take the -1 and put it right here, I'm trying to take the log of a negative number. That can't happen. If I put the 10 here, I'm taking the log of a positive number. That's okay. If I put the 10 here, 10 minus 9 is 1. So I'm taking the log of a positive number. So that's also okay. So it's a safe bet that the 10 is going to work. I can't take the log of a negative number. So you have to take your numbers and plug them back in to make sure that doesn't happen. All right, now, that's how it works. If you have a log on one side and not the other, you simply compress it to one statement, to one log statement, and exchange it for an exponential. If you have logs on both sides, you don't actually have to do that. Okay? If I had log of x plus 8 minus the log of x plus 1 equaling the log of 6, I still need to compress this into a single log statement over here on the left. So subtraction, turn back into division. And now I can use the fact that logs are one-to-one just like exponentials. So that same property that I stated earlier for exponentials works The exact same way with logs. I can now assume that since a log is equal to a log, same base, 10 and 10, I can assume that the expression is equal to the other expression. Right? Again, I didn't come in here and cancel out logs or something like that. I used the fact that logarithms are one-to-one to make this assertion. Now I can solve this equation. I can multiply both sides by an x plus 1, cancel, move the 6 to the left, the 6x to the left, move the 8 to the right, and divide. Okay, and again, you need to make sure that the answer works when you plug it back in. And it will, all right? But things that you can't have, for example, since you have an x plus 1 in here, you could not have any x's that would make x plus 1 turn negative, make x plus 8 turn negative. As a matter of fact, you'll notice here that you have an x plus 1 in the denominator of a fraction. So the next value of negative 1 is not allowed either. Not just because it was in the denominator of a fraction, but because it would mean you were taking the log of 0 up here, which again, is not allowed. All right, so you do need to be in the habit of plugging integers back in to make sure they actually work, because you will encounter ones that don't.